So in today's lecture, we're gonna cover four topics. Because the name of today's lecture is axial loading, we first have to define what is axial loading. After we talk about axial loading, because most mechanical material property are determined only by axial loading experiments, we'll discuss about typical characteristic of ductile and brittle materials and their axial loading results. And as a third topic, we'll talk about normal stress due to axial loading in detail. And in the first topic, we'll talk about so-called static indeterminacy problems. Yeah, of course, here I somehow use a fancy word, static indeterminacy, but actually, if I just rephrase this, you can just think about this as a type of problems that can't be solved by freshman physics knowledge, where you only assumes like a rigid body cases. Okay, so remember that we have done statics review. What I mean by statics is obtaining the force equilibria and moment equilibria by solving for unknown force and torque. That's what we call as statics. And there are types of problems which cannot be solved only with statics, and that can be only solved by considering the material deformation. Okay, so we'll get into the detail of static indeterminacy soon. Okay, so as I promised, let's discuss about the definition of axial loading. So suppose that you have this rigid wall and you have deformable circular cylinder here, and suppose that you have like many different forces, like this P1 force which gives tension, P2 force which bends this cylinder, T1 force which make a torsion here. You can imagine any other force. You can make another torque T2 that try to twist this guy. Okay, so you can imagine a lot of stuff. And given this kind of forces, our textbook choose typically these kind of coordinate system. For most problem you're gonna see in our textbook, x direction will be the axis of this pillar, and y and g would indicate the cross-sectional area. Okay, so these are the directions that's parallel to cross-sectional area. X will be the direction that's perpendicular to the cross-sectional area. Now, given this kind of force, now suppose that you are making a imaginary curve and you are imagining a imaginary cross-section, and to make a mechanical equilibrium, suppose that you are taking these apart. This is the yellow cut, and you have a P2 here, P1 here, and T1 here. You need some sort of reaction to make a force equilibrium of this imaginary body. Okay, and the reactions to make a mechanical equilibrium, force equilibrium, and torque equilibrium for this imaginary body actually can be categorized into four. And what we're gonna do is we're gonna categorize the reactions acting at the origin of YG or centroid. Okay, we're gonna consider like all reactions acting on this centroid point of this cross section, and at centroid point we're gonna assume like a V, M, and T, four kind of reactions. If we assume like a two forces and two torque, we're gonna find that we can make a satisfy force equilibrium for any kind of loading. Okay, that's the four reactions that we're gonna study in ME231. Okay, so what are these four reactions? First, we can think about torsion at acting on this cross section. So this torsion somehow can be understood as a torque about x-axis. Now we have like a N normal force acting on the centroid point. So it'll be like either compression or tension. You can also think about torque M, or so-called M, acting on this centroid point, and we call this as a moment, and it concerns about bending, or according to this XYZ coordinate system, it's torque about g-axis. Okay, so please see here you have torsion, which is torque about x-axis, moment, torque about a z-axis acting at centroid point. Now you have shear force that acts on the parallel to this cross-section area. Okay, so these are the 4 reactions acting at centroid point, and which is necessary to make a balance with these kind of external loading. And by obtaining this reaction forces and torque, you can see that these two are torque, these two are force, these two are torque. By considering these two force and two torque, you can always find like a mechanical equilibrium conditions. Okay, and what is the axial loading? Axial loading is the loading such that the loading only induces like a non-zero n, but all other reaction must be 0, like a torsion 0, shear force 0, and moment 0. Okay, in this case we call such loading as axial loading. So let me show you some examples before talking about example of axial loading. Let me give you the definition. The definition of centroid is the center of area, and if you are confused about what is the center of area, please recall the concept of center of mass back in freshman physics. So back in freshman physics, what you have done is when you obtain center of mass for x, you have done this calculation, right? This is infinitesimal. This is infinitesimal mass and this is total mass. Okay, for obtaining centroid, instead of mass, you simply do infinitesimal area and total area, then that will give you centroid point. And for example, this guy would have centroid point here. Sorry for bad drawing. Okay, so if this is cross section, you can see centroid point maybe here. Okay, now after making the definition of centroid, let me give an example of axial loading and non-axial loading. So if you consider a force acting on this centroid point for this circular pillar, circular cylinder, you can see that whatever imaginary cross section you choose, you can see that the reaction only have this kind of normal force acting at exactly centroid point. However, if you consider a circular cylinder with a similar tensional force acting at this end, at the side wall of this kind of axial loading, what you're gonna see is to make a mechanical balance with this guy. This is the green point, and you have red force here, you have imaginary cut here, and to make a mechanical balance, if you only have force acting at centroid point, you're gonna see that there is finite torque, so that this guy want to rotate in clockwise direction. So you need moment to counterbalance this kind of thing. So because you need both moment and normal force acting as centroid to make a balance, you should not call this as axial loading. Actually, if you study the deformation of these two cases, deformation of axial loading always occurs in this kind of shape, only extension. However, deformation of non-axial loading would accompany sort of bending kind of definition. Okay, so when somebody asks what is axial loading, if you just look at these part, you may answer that okay, both of them are axial loading, but actually it is not. What you have to do is you have to make an imaginary cut for your cylinder under the force, and at this imaginary cut, you have to consider if you can satisfy mechanical equilibrium, force equilibrium, and torque equilibrium only with this normal force at centroid. If you cannot satisfy mechanical force, mechanical equilibrium with normal force at centroid, then you can say that it's not axial loading. Okay, so that's the message I want to deliver. So we have to define the detailed definition of axial loading first, to talk about what axial loading is and the definition of the relationship between displacement force under axial loading. Okay, so actually what you're gonna do in ME 231 would follow these kind of storyline. So what you're gonna do is following. So in ME 231, we will consider some applied loading. Applied loading can be two kind, force or torque. Okay, and given this applied loading at cross section, you're gonna have 4 kind of reactions: normal force, shear force, moment, and torsion. You can consider all of them acting on the centroid point. And given this reactions, force and moment, what you're gonna see is this normal force will result in normal stress, and this torque, so-called moment, will induce normal stress that is not constant over the cross-sectional line. So that will be topic of next chapter. In chapter 4. Then the torsion T would induce shear stress, and shear force V would induce shear stress. After obtaining normal stress and shear stress acting on specific plane, what you're gonna do is you're gonna make a connection between stress and strain in local point. And when make a connection between stress and strain, you're gonna use material property called Young's modulus and shear modulus. After obtaining shear modulus and normal shear strain and normal strain, you can obtain displacement and twist angle for your cylindrical body. Okay, so these are typical flow chart we're gonna do in our ME231. And of course, when obtaining these stress out of this reaction force and torque, you're gonna use geometrical factor like a cross-sectional area, area moment, and rotational moment, and thickness of the beam, and etc. Okay, so if you I think after midterm, if you can, if you can completely understand these thought process and explain these concepts one by one to your friends, then you are safe to get really nice score in your midterm, and you can think that would indicate that you are doing very well in solid mechanics courses. Okay, so when you are preparing midterm exam for ME231, yeah, please come back to this table and try to see if you can have like a unified view on this table, and if you can explain these concepts to your friends. Okay, so it will give you really nice summary for what you're gonna do in ME231. So what you're gonna do is before midterm we'll learn NMTB one by one, and we'll go through this process one by one for each reactions. And after midterm, what you're gonna do is we'll try to consider combined loading having NMTV together and see the deformation and stress state of the structure, talk about safety design and deformation of body under combined loading. That's what you're gonna do after midterm. Okay, so it'll give you some sense on what you're gonna do in ME231. Okay, so with this, let me finish my discussion on the definition of axial loading.